A few years ago, we got together as a team and brainstormed where we thought we could push forward the state of the art in real-time graphics. There were two key areas that stood out. The first, dynamic global illumination. Beautiful bounce lighting instantaneously.
I don't have to be constrained to do a game where the world has to be static, and I'm able to iterate a lot faster.
And we call this new system Lumen. And we're about to show you what it is capable of. But first, there was another area that we thought we could push forward. Truly virtualized geometry. The artist wouldn't have to be concerned over poly counts, draw calls, or memory. We could directly use film quality assets and bring them straight into the engine.
And that's a big deal for artists. I just want to be able to import my ZBrush model, my photogrammetry scan, my CAD data, without wasting any time optimizing, creating LODs, or even lowering the quality to make it hit frame rate.
In the end, that's what it's all about. Art that just works. And we call this new technology Nanite. Here is the future of Unreal Engine running live on a PlayStation 5.
Awesome, let's take a look at it.
This has to be the right way.
Before we continue, let's stop a moment and take a look at some of the key features of this demo. Much of what you see was built with Quixel Megascan assets, but instead of using the game versions, we used the cinematic versions, which would typically only be used in film. There are around 1 million triangles each, and thanks to virtual texturing, they all use 8K textures as well. Nanite can render an insane number of triangles very quickly. There are over 1 billion triangles of source geometry in each frame that Nanite crunches down losslessly to around 20 million drawn triangles. What does that many triangles look like? This isn't noise. These are the triangles, each a different color. Most are so small that they look like noise. Nanite achieves detail down to the pixel, which means triangles are often the size of pixels. This amount of geometric detail requires shadows to be pixel accurate as well, and Nanite can do that too. Speaking of lighting, all of the lighting in this demo is completely dynamic. With the power of Lumen, that even includes multi-bounce global illumination. No light maps, no baking here. Without GI, all of that beautiful lighting is gone. With Lumen enabled, we can move the light and the bounce changes instantly. Okay, let's keep going. We've made some great additions to our audio system as well. Convolution reverb allows us to measure reverberation characteristics of real spaces, like actual caves that we sampled, and reproduce them in virtual spaces. Sound field rendering allows us to record and playback spatialized audio.
Okay, so that'll give you, start to give you a taste of some next generation types of features. We're gonna cut back to the slides here a second. Let me go back to share. So there's some interesting things coming down the pipe, and I think that video from Unreal Engine is really kind of giving you a true sense of sort of a generational leap from what we have now. But going back to more, where we have been in this last generation, let's do this. Let's take a look at what features that really brought to the table. Right? I think we kind of covered this already. Global illumination in some sense. It's not completely dynamic like what we just saw in that Unreal Engine demo. For instance, Unity has a way to add elements of global illumination as long as well, obviously you can have baked lighting if nothing's moving, but Unity takes it a step further with their system such that as long as the geometry is not moving, you can allow the lights to move and still have stuff bounced around. So it's kind of like these things can be accelerated by keeping things constant. You can make more assumptions and do that kind of processing. But the next generation will obviously remove a lot of these limitations in various different ways. So there's the physically based rendering, right? We talked about that. You can have day and night cycles and everything should just work because the amount of light that hits an object can't generate more light, right? You're limited by the actual amount of light in the scene. And then in this generation, of course, we had the launch of mainstream VR devices, right? Oculus and HTC Vive launched in 2016, and the first phone VR, I think that was out, was it 2014-ish? So things were kind of getting off the ground there, and Unity was definitely at the forefront of supporting that. I think something like 70% of all applications, all VR applications are made with Unity or something like that. It's kind of ridiculous. Also at this time, threading, on pretty much most, if not every engine out there could take very strong advantage of the multiple cores that you had in your box. And also, I'd say for probably the first time, Unity was definitely at the forefront of this one as well. It's the idea of being able to support a variety of platforms. We kind of take this for granted right now. You're used to using Unity and you think, well, I want to build this for my iPhone or my Android. You'd be like, okay, well, let me make a few modifications. Maybe it's a day's worth of work, maybe, or depending on the scale of your application. But it's certainly not anywhere in the realm of rewriting it from scratch, right? It's kind of a more minor kind of thing that you have to do. And if you have it in mind from the beginning, it's very little extra work. And that's something that we didn't really have before. Typically, and still what often happens today, is that developers are contracted to take one studio's game that they made for PC and then port it over to something else like the Nintendo Switch. That's probably a really common example, and it requires a lot of expertise, because if you're writing this high performance application that's meant to run on this beefy PC, and now it has to run on this basically mobile machine, right, the Nintendo Switch, there's a lot of concessions that have to be made and a lot of customizations that go into making that happen. And typically, most technology sets don't do a fantastic job of serving both the high end and the low end simultaneously. In fact, historically, if thinking back to Unity, Unity has actually been mostly targeting the low to mid end. Like AAA high-end gaming has not, for the most part, been done on Unity. This is something that's kind of been evolving and changing, and I think in the next, I don't know, 1 to 5 years, that will likely change heavily based on what Unity is up to. And then, they will be doing an amazing job of serving, every end of the market, which is an insane amount of work. And they have an insane amount of developers. I saw it written somewhere they had something like 300 engineers spread out across the world, and that's kind of insane. When my group right now, when I first started working here at MPS, it was to build applications and develop an open source game engine called Delta 3D. And from 2001 to 2012 or so, that engine was getting pretty constant updates from us and some of our partners. But at a certain point, it didn't really make sense for our small band of developers, right? Like a dozen people involved at max, doing it part-time while they're trying to do other contract work. Didn't really make sense when there's companies like Unity or Epic that have hundreds of developers, and they're offering you something for either free or ridiculously cheap. So I guess that kind of brings us to the last bullet point right here. Oops, I didn't want to do that. No. Which brings us to free and cheap licensing and availability, right? this is another thing that, we tend to take for granted right now. It's like, you want Unity, just download Unity. And if you're using it in a more professional sense, you might have to pay, I'm not sure what it is now, like $1,500 or so for a license, which, that's like less than a man week's worth of salary. And, you can't even come close to producing something like that on your own. So that's extremely cheap. And also just recently announced, Epic Games is allowing anyone to use Unreal Engine 4 completely for free until they've made over $1 million. So, like, it doesn't really get any better than that. It's an amazing thing to have, and you really have very little to lose by going with that. Unreal, though, as opposed to Unity, has been much stronger in the high-end markets, and they tend not to cater quite as well to the lower consoles. But again, they've been broadening their reach as well. Okay. Also, during this generation, we saw the ability to take animations that were made for one character and then bring them over to another one, right? Pretty much this whole page is just stuff that you don't think about now because we take it for granted, but it really just wasn't there before. You can imagine we go to Mixamo right now, right? And you see that little prototype guy that's doing the animation. You download it, you apply it to your character that looks completely different, and somehow it works, right? That was not a thing at all until the game Spore came out. When was that? Geez, probably 10 years ago. But there was a lot of technical work that went into finding ways to basically bring animations that were specific to a skeleton, right? And then use them on a different skeleton. And over the last 5 years, pretty much every engine has finally got this, or at least any engine that's for mass use has this sort of thing to make it easier for people to come and get their animations and not have to author them specifically for the model. Also, with all this great power comes some great responsibility, and it can be pretty easy to do things inefficiently in an engine. So engines are kind of just providing more and more tools to allow you to do everything you need to do, from the design of your application all the way to delivering it. And they just keep filling in more of those gaps. And to keep your performance and things in check, there's built-in profiling has become a pretty standard thing at this point. Before this time, you had to use really expensive proprietary stuff, of which we also had here in Moves. I forget how much we paid, but we had some some profiling software that we would use on our other software to figure out what's going on. But at this point, you can, for the most part, count on whatever engine you use probably having something there to help you profile and know where things are going on. And if there's interest later, we can look at this in more detail in Unity. So that was only part one. Like, a lot of stuff has kind of exploded, as we go through each generation. The second aspect of this is that we have not just HDR in our computations, right? It's not just that we're using, a larger range of numbers for our colors when we compute stuff, but now our displays actually can display more of that stuff. So that requires some extra support, and pretty much all engines have to have some support for that at this point, especially since there are a lot of 4K TVs out there with HDR support, and the current crop and the future crop of consoles are very much expected to be running on those displays. But of course, more pixels don't come for free. That's always kind of a problem. And if you want to go from 2K to 4K, that's actually 4 times the amount of pixels. So that's kind of asking a lot for your hardware. And oftentimes, 4 times the amount of pixels is not like 4 times clear, right? It's perceptually, it's a bit better, but it's not dramatic. It's kind of, you have this diminishing return on the value I think you get for more and more pixels. But in any case, there are a lot of methods that really try to, get the best perceptual results without paying the full cost, right? If you have 4K and you actually render all those pixels the same way, yeah, you're going to pay 4 times the cost, essentially. But one of the mitigation strategies that was done with this, with the current generation, is something called checkerboard rendering, or basically just, it's like a kind of a, they're upscaling techniques, but they're upscaling techniques that use additional information to make smarter choices about how to do it, right? It's not just blowing it up and making it bigger and blurry, right? It's actually trying to infer what those pixels might have been. For instance, you could see that here's potentially a render texture, and the whole texture right in here, right, is for a 1080 screen. But let's say you're on Xbox One and it has some kind of weak hardware and it has trouble pushing out 1080p at 60 or 30 frames per second. Well, what developers will do is they'll dynamically change what they're rendering. Like they might say, you know, instead of rendering the whole 1080, I'm just going to scale this back on the horizontal and do like 90% or 80% of it, right? And so they render at this 80%, and then they upscale from that, the part they rendered, back out to the 1080. So the upscaling process tends to be very cheap compared to like lighting, doing all the lighting calculations for a pixel. So based on what the current performance is doing, the size that it's actually being rendered can change. And you might notice this, especially like if you if you're trying to run VR on a laptop, is where I last was very much made aware of this. You know, it might be struggling trying to maintain 90 hertz, and it's just struggling to do it. So it ends up scaling down how much it renders to, and then blows it back up, and then things look pretty blurry when that happens, if this gets small enough, right? You can probably go to 90% or 80% without too much of a loss in quality. The other technique that's interesting and is built into the PlayStation 4 hardware is this thing called checkerboard rendering, where you pretty much just render these checkers, and then you use the neighboring pixels along with a velocity value, like they're kind of tracking where pixels are going and coming from, and doing some other bookkeeping to then regenerate, you know, maybe all these green ones, for instance, and then you end up getting something that looks quite a bit better than if you you know, you just rendered at 1080p and went to 4K. Instead, you could do this checkerboard rendering, which essentially cuts it in half, right? Instead of going 4 times the pixels, now you go twice. And then you reconstruct and you get something that looks quite a bit better without paying, you know, kind of an insane cost for it. I think I'll come back to these in a second. I want to show you a little bit more what this looks like. So, okay, you could kind of zoomed in. This might be 1080p. And if we upscale that to 4K, you can see, all right, we got some softening to all the edges, and it's not crisp, but then, you know, like 1080p would have looked okay if you were looking at it on a 1080p display, but blown up, not so much. Now, if you went to 4K, right, you get things look sharp and they look pretty good, but here's kind of a middle ground. It's that checkerboarding technique that's going to give you something that's quite a bit better. Like you can see the edges here just look a lot less sharp than if you compare it to a normal 1080p upscale. So this is like one flavor of kind of high resolution cost mitigation. In the next generation, we'll talk about another one, but developers are constantly looking for, you know, ways that they can get away with high perceptual quality at a low cost. And this is just one of the tools in the bag that has become very prevalent in this last generation. Also, interestingly, throughout this time, there's been a huge advance in being able to compile from one language to another language, like transpilers, where people could now take a game engine code that's written in native C, C++, and convert that into something like JavaScript, right? That's the whole reason that Unity WebGL can even work, is that they take the whole engine code, they crunch it down, and then they're able to put this in a format. I mean, initially it was a flavor of JavaScript, but now there's something called WebAssembly, which is kind of like it's like more like a binary for the web. You could think of it. It's still character based, but it's coded, and it's a lot smaller than writing normal code, right? It's not for humans to write. It's more a target for code that's written in something else to be compiled down to it and then be able to run in the web. So going with Atwood's law, which is not really a law, but jokingly says anything that can be written in JavaScript will be written in JavaScript, and this is very much in line with that. Game engines, emulators, like whatever, that there's this is kind of a big mechanism for making that happen. And I think at this point, Unity WebGL is in a pretty good place. For a while there were limitations on threading, but I'm not sure what the state of that is. It's probably okay now. But it's an interesting avenue, like web is just, it's everywhere, it's ubiquitous, everybody has it, it's a target that everyone can count on. And in a way, I think a lot of times we can look at the web is just another layer in a tech stack. So if I come down to this right here, right, you can imagine, well, there's hardware, there's drivers that know how to talk to the hardware, there's the operating system that knows how to use the drivers, and you have the APIs like WebGL or anything that's kind of like a standard way for software to talk to your graphics hardware, and then what happens under here can be specific to the hardware. On top of that, you could think about the browser, and then there's a game engine and your application on top of that, right? All these things are just layering from low level to high level, and the browser tends to be a very common part of the computing stack you just see nowadays, right? It's like you're making an application. Well, that I'd say at this point in time, a web application and a regular application, the distinction is really shrinking. Like, I don't know that that'll be it. I mean, it would be important, but I think just using the word application is equally valid for both. So let's come back here. Okay. Also, in this period, we've had quite a number of advances in the ability to create geometry through capture, right? We touched on that a little bit in graphics. And one of the big things that's happened right now, and where that the geometry from that Unreal demo we just saw at the beginning of class came from, was from this technique called photogrammetry, right? So it's like taking measurements in photos. If you have a bunch of photos that overlap in the way they're looking, there's a bunch of crazy math and algorithms that can kind of reconstruct three-dimensionally what it sees in those photographs, kind of under the right conditions. So people that are experts in doing this kind of thing, right, they might have gone into that cave that we saw in the demo or something like that, right? And then they took a bunch of images around there and then brought it back home and did, let their computers crunch on it for a couple days, and eventually it was able to kind of put it together, and then they could clean it up and have something that looks really photoreal, because that's where it actually came from, right? It wasn't authored trying to make it look photoreal, right? You don't have to be Rembrandt or something trying to like create this thing. It's like, well, I can just take a picture, like anybody can snap a picture on a camera. Bill last week pointed me to a mobile application called display.land, which basically lets you do the same sort of thing, right? You can download this app for your phone, and then you pretty much take a video around an object, and it can be smart about how it takes images out of the video to get a good amount of overlap, and it'll generate a textured mesh for you. So that's pretty cool, right? It's in everybody's pocket at this point. Although getting good results of that does take a lot of expertise and know-how. But this is a important piece, I think, in the push for photorealism. And also, I guess, to piggyback off that, photorealism is good for games, of course, but there are so many use cases for game engines at this point that I think really in the next generation, as we'll come to in a second, the term game engine is just kind of will be still used, obviously, and still have the same meaning in some sense, but the word game in front of the engine is no longer like that meaningful, right? There have been and are people right now that are producing various films in Unity and in Unreal. And on top of that, not just, instead of just making the whole movie in there are compositing systems that are used, and even in high-end production. For instance, I don't know if any of you guys saw The Mandalorian Star Wars series, but instead of having a green screen behind them, what they had was, the Unreal Engine rendering the backgrounds, and then the actual camera that was going around was tracked so that as the real physical camera was moving around the actors in the set, right, the background LED screens would actually change based on the viewpoint, right? So you would get something that looked realistic, and then they could kind of blend it in post-production and make things look great. So I think it's definitely found a home in film creation in a number of aspects, but it definitely goes well beyond that. And I think prevalent at this point is that you can expect most mainstream kind of game engines meant for like mass consumption, or just really popular game engines you can expect to have some sort of editing capability supporting this, right? Like a nonlinear editor, which just is have multiple tracks and crossfading and doing all whatever film types of stuff you need to do. Another one that we have here is the idea of a GPU-based particle system. Now, that when we saw those particle systems up until this point, you could have tens, hundreds, maybe thousands, and kind of get away with it. But after that, if it starts, as soon as you start to get to like 10,000 and above, then you're going to really have a severe impact on your CPU, which is the thing doing all the work. Now, what people have done instead is actually do the simulation in shaders, right? So they have a special way of writing code such that they can keep track of where particles are from frame to frame and update them all on the GPU, right? One way to think about this might be to think about render to texture, right? When you run a shader on something, let's say if a particle moved from point A to point B, well, then I know in the next frame I need to go from point B to somewhere else, right? I shouldn't start back at point A. And so you could either do this by having, it follows some sort of predefined function, right? So you could just take it at a different time. Or second, you could actually just store your results from the previous frame in a texture and then load them in the current frame and then make your results based off that, right? So this sort of thing would basically allows particle systems to scale from having thousands to millions of particles on the screen, and you can really change, do some more spectacular looking things when you have that. And Unity does support this. It's a kind of a newer thing called the VFX editor. And we can take a look at that later if you guys would like. Okay, so let's look to the crystal ball here. I kind of split this into the things that I see are like they're for sure, and then there's the things that maybe there, maybe not. I don't really know. It's obvious that path tracing, ray tracing is kind of here and now and will be very prevalent in this next generation, considering we know that both the new Xbox and the new PlayStation both have support for it in their hardware. So that's here to stay, and there will just be more complex sorts of render pipelines that use both rasterization and ray tracing to kind of complement the strengths and weaknesses of the system. So those are definitely there. VR, AR editors, right? Instead of just making stuff for VR and AR, there will be a lot more editing that actually happens inside of those things. Both Unity and Unreal have, they both have editors that you can actually build in VR already doing that sort of thing. But they still have a way to go and mature, and I'm not really sure what the current state of that is, but that will only get better. So for the past, we've had these new graphics APIs. Oh, let me check the chat. Ship bridge inside of VR. Oh, cool. Well, I'd like to hear about Joe's editing his ship bridge in a VR editor. Last time I tried it, it was a little janky. Low driver head APIs, right? Director 3D is the Microsoft API. There was OpenGL was kind of the open one, but OpenGL, its next step is kind of to more or less abandon. It's not, kind of what it has with OpenGL and change the future of the way it works using something called Vulkan. And the idea of these APIs is just that it makes them even more verbose and puts a lot of things that the driver used to be responsible for in the hands of the developer, which, given the right know-how, can result in some large gains. But up until this point, Unity's Direct 3D is still experimental. I think it's been experimental for several years, and like a lot of performance reviews that I see from other engines, often are very underwhelming. So I think that all of that is going to get solidified and improved here shortly. And let's see, on the web side, right, instead of going from WebGL, the next aspect will be more along these lines, but it's called Web GPU. But the web, I think Web GPU will be made to be more accessible. You might not have found WebGL to be that accessible, but believe me, compared to OpenGL, Vulkan, or any of the rest of those, like that was definitely pushing the easy button in comparison. So that's just extra tools that will allow developers with the know-how to really squeeze the most juice out of their systems. Next up, we have asset paging systems. So even though GPUs are really powerful and they do a lot of stuff, there's still a lot of wasteful things that are doing. You might be able to imagine a character, the really detailed character, only you don't see the character standing next to you. You see them like, like a couple thousand meters in the distance. So they're a handful of pixels. Well, for this character, you're what? You're storing, I don't know how many megabytes of textures and geometry so that you can see those handful of pixels, right? That's kind of like the extreme end and doesn't really necessarily make sense. But all those things are still consuming memory when they don't need to. So the idea of making something virtual is to say that, hey, I have some magic way of having a version of my assets that maximizes what I can actually see, right? So with virtual texturing, you would have full textures for most of what you could see, and then there would be like lower res versions for stuff in the background, and that would be like your current source of things. This also enables the ability to texture things much more uniquely, right? Instead of having to have this repeating texture over your terrain that can look pretty obvious, instead you could have a texture that's different across your whole terrain, and the system is set up to where it creates all the pages and the chunks and everything so that it can pull just as much as it needs for what you're looking at for the most part, without needing like let's imagine you have like I don't know, instead of a 2K by 2K texture, imagine a 200K by 200K texture. You can't fit that in memory, but it could be like cut up in a really special way such that the stuff that's right next to you has a bigger chunk of that memory, and stuff that's farther away has less. And the same kind of idea is applied to geometry streaming, which we kind of saw in that the Unreal Engine PlayStation 5 demo. If they have a billion triangles, well, hardware is not going to be pushing that out anytime soon, but it can handle a few million. So if it has some magic way of like pulling in and out into memory just the right thing you need while you're looking at it, you can get away with things that are just extremely finely detailed. And there's a lot of secret sauce that goes into that kind of thing. And these developers have been working on this for many, many years. That PlayStation 5 demo was, I think, some guys, was it master's or it was a thesis project of some sort, but he started that thesis like 6 or 7 years ago, I think. And virtual texturing, was actually originally done by John Carmack again, the guy from Doom and Quake. And at least that was before he jumped over to Oculus and started working on VR. And, that allows you to, once you get the kinks worked out, really increase that push toward photoreal. So next we have procedural AI assisted creation tools. So yeah, procedural is one of the ways you can make things, but one of the things we haven't really talked about so much is using AI or neural networks to come in here and assist with that. Unity bought up a company or two that actually produces this sort of thing, and we'll see some stuff in the engine at some point that will allow artists to, basically, you can imagine you have a texture that you took from a photo, right? And in the photo, it has something you didn't want in there, right? Let's say you're looking at grass and there is this like big patch of weeds inside of your grass texture. Right? So AI could actually come in here. You could tell the AI, hey, I don't like those weeds, scrub it out, and then based on what it sees around the image, right, it could fill it in and just procedurally, make a good guess at what that should look like. So you can imagine neural networks coming in here to assist with all kinds of little tweaks and different things like that. And we will definitely be seeing that. And all of this helps artists, it helps designers, and it reduces the iteration time to produce something, right? And that's kind of what game engines are there to do. And we're just going to see more and more of things that result from that philosophy going forward. In this generation, you'll see more things supporting streaming systems. I'm not a fan at all of Google Stadia or any other streaming systems because, if you have to, for those of you guys that don't know, these remote playing systems are kind of like a computer somewhere in the cloud on a server runs your game and then sends you the video of that game, and you take your inputs on your mouse and keyboard and you send it to the computer, right? And that sounds fine, but you have the round trip time for your input and the video, and that creates a lot of latency. And under the right conditions, latency can be acceptable for some cases. But if you're trying to, if you need to rely on it, or you want something that requires quick reflexes, then that doesn't work so well. In a way, I think a better use case might be for something like developing on the HoloLens, where I could run what I want the HoloLens to do in Unity on my PC, and then, just have the HoloLens be moving around, locating itself in the world, and letting the PC know what's going on. I wouldn't be surprised to see this sort of thing happen. Looking into my crystal ball, with Apple making a pair of augmented reality glasses, where pretty much all the computing power is going to be in a much more modern iPhone, where the iPhone actually streams the overlay video, images to your eyeglasses that display that to you into your eye. And that's probably at least a few years away. And then, of course, more high display mitigation. There's this idea of variable rate shading, where there are some smarts on the video card where it could decide that, hey, this is a very low contrast area of your screen, right? If you can imagine you have a green box and the color isn't likely to vary very much across the surface of this box, well, it could just, it could pretty much render at a lower resolution and then fill that in. And that's pretty much what it does, but in a smarter way. So this is already supported on the current generation of PC cards. This will be supported on the new Xbox, and I haven't heard anything about the PlayStation. But it's another resolution cost mitigation technique. So last piece here, the future, right? Fluid simulations, not something that developers have really been willing to allocate much of computing resources to do, but that's getting easier and easier over time. And at some point, I think there are going to be some interesting ways of doing that, and having fluids be a more normal part of what makes a physics engine. Like right now, when we think of physics engine, that's more or less limited to rigid body physics, right? There are people who do stuff with soft bodies, like jello-y stuff, but those aren't like really standard parts of game engines. Those are more specialized creations. And there's, of course, there is some small scale water stuff, moving through puddles and whatnot, and ocean rendering to some extent, but that's not necessarily what I tend to think of as fluid simulation, right? That's kind of a special case where you're doing stuff, to make waves in a believable way. You're not simulating a bunch of particles of water like you would in a fluid simulation. Real-time collaborative editing. I keep waiting for this one. I think at some point this will be more of a thing. I think once the network infrastructure is strong enough to support uh, more use cases and people can depend on it, I would imagine that you could be using Unity working on the same scene as another person using it, right? At some point, we're going to see more and more of that sort of thing. Also, when it comes to photorealism, there's this idea of something called a light field, where instead of just storing the color of light that comes in a particular position, you also know the direction. And if you know the direction light's coming from, you can kind of work backwards in a way and reverse engineer what a sort of volume around that would actually look like. And there are some companies that are doing some pretty interesting things with that, and I think you're gonna hear about that much more in the future. And it enables some pretty interesting things. I mean, imagine you had your camera, right? The camera only takes color there, but if it knows the direction of the light, then it's like, in a way, you're almost taking a 3D picture. You can move around the viewpoint and see a little bit more after the fact. So that's kind of ripe for exploitation in the future. And then you have the ability to destroy objects, right? Make them break apart in believable ways. So these are either voxels or something called a finite element system. And these have been specialized things that have been used, just kind of lightly here and there, but it's not really something that had mainstream support. Unreal Engine is getting this very soon in a bigger way, and I think at some point Unity will follow suit. And then I think the one that is probably not on most people's radar that I think is a good one to turn your eye to is how blockchains can be applied, for simulations, for games, for whatever. So the blockchain, I guess if you're not familiar with the idea, right, this is the technology behind Bitcoin and other digital currencies. And the idea is that instead of just being able to copy paste everything you can digitally, because it's digital, right, it creates an element of digital scarcity where your bits could be unique in a sense. It's like, hey, these are my set of bits and you can't copy paste it, right? I actually have ownership of that thing and it's unique to my possession. And this is going to be enabling some different things, right? It could be used in inventory management. It could be used for capturing statistics on an experiment. Like, I don't know, there are a lot of different ways to do this, but it helps you create a system that can be dependable, decentralized, kind of just very transparent. And I don't know, I think you get a lot of guarantees by having that digital scarcity. You can have some sort of guarantees about certain things, and that'll be important in a lot of different workflows. So a trivial example might be, hey, I have a game where I have unique limited time items that I give out, right? But you might also have I don't know, off the cuff here, I'm running an experiment and I capture this data about an experiment, and that goes on this blockchain, and it's anonymized in a way where you can't identify anyone, and you have that kind of guarantee built into the system. But I don't know. I think if you really think about the use cases, there's a lot of room for there's just creative opportunities with that. One interesting aspect of this is that there's a company called Otoy right now, they do like high-end rendering for films for the most part. And they have their own render farms, right? Their machines of GPUs and CPUs to crunch this out for people as a service. But one of the interesting things they're doing right now is that you can pretty much sign up to allow your GPU to be used by them as part of like this worldwide cloud, this render farm at global scale. And in exchange, right, they're going to give you a cryptocurrency, a crypto token for, basically proportional to the work you do in the system. So, it facilitates something like that. You could possibly imagine, for your game, right, that you could crowdsource various things for that. And if you needed to make a survey or something like that, I don't know, like one way, if you wanted some sort of information, right, you could probably exchange some sort of token in exchange for people around the world participating in whatever your system is. So I don't know, definitely something to look at. And I'm sure there's going to be some creative uses of this when it comes to games and simulation. So there's a software stack. Choices, this doesn't even come close to showing all of them. There are like so many, right? I think perhaps the way you're going through this right now, you think, well, what are my choices? Unity and Unreal? Well, those are definitely great choices and probably the ones you should pick, but you probably heard of VBS, Virtual Battle Space. They're about to release VBS 4. And if you have something that really relies on a lot of military equipment and military type scenarios, there's a lot of stuff there to facilitate those common use cases. If you have a first person shooter that you need to do for something, definitely take a look at that, because that gives you a lot of stuff right out of the box. But there's tons of options. And really, one crude way of looking at it is, go by the 3 things: cheap, fast, and good. Well, pretty much everything is cheap at this point, relatively speaking. So that's kind of amazing. Fast, well, some of the best ones are, they're quick to iterate and produce things. Maybe if yours is very military oriented, in a heavy aspect, then VBS might be just already tailored to do what you want to do already. So that would make that even more fast than what Unity or Unreal allow you to do. And then, of course, there's good, like how good do you want your thing to be? And typically, these are always some sort of trade-off to be made, but at this point, an argument can be made for all of your choices here. Maybe, in a sense, you do get all 3, but how good, how fast, how cheap, I don't know. Like, you could imagine going for fast and good. That might be, well, I'm going to use Unity, and I'm going to outsource all of my artwork to someone and buy a bunch of stuff off of the asset store, where it makes sense, and just put a bunch of money out there. And in that case, it's not cheap because you got a bunch of people on the side to do something, but you got there very quickly and good for, hopefully. On the other hand, it could be like cheap. You're like, I'm not going to pay for any art. I'm just going to use whatever I find on the asset store or free on the web, and I'll use a game engine that's free and provides a bunch of stuff. Well, all right, but how good is it going to be? The underlying mechanics of what you produce are probably pretty decent, but you probably have a bunch of art that looks like it's very inconsistent, obviously not made according to one cohesive vision. So I don't know. Like, I think you kind of have to resurvey the game engine landscape, often enough to kind of make decisions like these. But for the most part, you're not really going to go wrong with Unity and Unreal. Unity. So I guess I should point out other aspects of modern game engines you often find now. Besides this wide-reaching deployability, right? There's generally kind of an ecosystem of sorts that goes along with it. And Unity and Unreal are again the poster childs of this, right? You're probably all familiar with Stack Overflow or question answer sites. Well, there's Unity Answers, right? This is one specific to Unity. You got the store that's specific to Unity, instead of just going to a random, website or, Turbo Squid or something like that. You have this storefront that's just for Unity, and then you have, a rich section of documentation. So, documentation is often very poor in a lot of cases. And I used to say that Unity's documentation was pretty good, but lately things seem pretty poor. I think they're just going through a lot of growing pains, but that's probably only a matter of time. So all of the different supporting underlying features are something to consider as well. Like, you might find VBS 4 is great, but if you go look for VBS 4 help, yeah, probably you're going to be crawling through some forum hoping for the best, and I don't know, you may have trouble going that route. Whereas the communities for Unreal and Unity are just massive, so you'll be able to find answers for most things relatively quickly. And That